This is Edmund.
This is Edmund.
PD. Okay. I see. Very nice. Solver course.
Probably make some modifications. He probably will make some modification based on what you cover.
Really?
So
Okay.
in a separate email he sent me, said he will do some adjustments to
I see.
include FNN inside.
Okay.
Yeah, it's pretty good.
Okay. 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 So, good morning. This is the third day of the fast multiple method introductory course. The previous lectures are already online. So if you go to this website for this course, Short Courses for Scientific Computing, then there are links to the previous lectures. Also, the hands-on session is from the link too. So you can go to these. Yes, thank you. You can go to these sites, and you can see the. You can see the thank you. You can see the videos from here, and also from this link, you can actually go to the Google Drive for the code. And I made some modifications to the codes I did live. So because I coded live, there were some mistakes, and also there were some parts where it was not so clean. So I cleaned up the codes. Now we have step 1, 2, 3, 4, 5, 6, 7. I did it in 7 steps. So each step is now much more readable than the previous ones. So there's no sudden change. I gradually changed the codes so that you can see very easily the difference between the previous. So first, before starting today's topics, I thought I would first review review the codes that I made, that I changed. So if you go to the website, you can already download step 1 through step 7, and I will briefly outline what is in the code. So maybe I can actually open the code as well, so that you can see what's happening inside the code. So here I will show the code, and I'll switch between the slides and the code so that you can see what I actually changed. Okay, so first, step 1. I didn't change too much in step 1. This is almost the same. Yeah, I don't think I changed anything here. So this one is still this problem here. So far field approximation, and this goes from step 1, calculate the sum of Q. From that sum of Q, calculate U prime. And from UI prime, calculate UI for all the points. So sum charges, calculate effect, center source on center target, and then assume all targets in the box have equal potential. So this hasn't changed. This code is the same as the previous one. But step 2, I changed a little bit. So step 2 now, instead of that copying and, I did some strange copying of the original box, so it wasn't doing what this picture was saying. But now, step 2 is actually doing exactly this. It's doing the near and far field decomposition by dividing the domain into 16 boxes, and for each blue box, it's calculating the red box with the far calculation and the other ones with the near equation. So I will show you the code that does this. It's not so much more complicated than the other one. So if I open it in this buffer here, you can see the difference between step 1 and 2. So this one is step 2. This one is step 1. So step 1, far field approximation. Step 2 is near far decomposition. So what happens now is here we had xi, yi, and I and j were separate points because they were in separate clusters and they weren't the same points. Now we are using the same coordinates for the x and I. They're in the same region. It's just divided into 16 boxes, and the far ones are calculated with the far interaction, and the near ones are calculated with the direct equation. So we just now define only one x and one y instead of xi and xj and yi and yj. So now we have like this. And ui is initialized to 0, qj is initialized to 1. And here, before I introduce the concept of multiple and local expansions later on, but in this example, I just decided to do the following. So for each box, you have qj prime. I am going to call this m, and also I'm going to number this according to the two indices, ix and iy, which is the two index for, that goes from 0 to 3 in each direction. By doing this, I don't have to use the Morton index and go back and forth and map it. I can just keep using this two-dimensional index to index which box I am discussing. And the calculation then becomes very easy. So maybe I should have realized this yesterday, because it would have made the code much easier to understand. So now I can do something like this. X times 4, because x is a random number between 0 and 1. If you multiply by 4 and turn it into an integer, it's a number between 0 and 3. Also, iy is between 0 and 3. Now, I can directly index the m, because the m has two indices now, the ix and iy. So in the domain I'm showing in this picture over here, this is 0, 1, 2, 3, and xy is 0, 1, 2, 3. So by having the two-dimensional index, I can point to any box in the domain by using ix and iy. So that I decided to do it that way. And now this m to l part, which was very ugly yesterday, becomes very, well, not very clean, but somewhat more cleaner. So now I just have to loop over ix, iy, and then jx and jy. So this loops over all the boxes for the blue box, and then it loops over all the red boxes. Let's call them jx and jy indices. And now, instead of doing like the parent of the parents, neighbors, children that are non-neighbors, now I can just examine everything, all the combinations, and check which one is actually far. So this is, if this distance is larger, the absolute value is larger than 1, or the absolute value of iy and jy is larger than 1, then that means it's far enough. So it was easy to check this because I'm looping over everything, and now I just need to compare ix and jx. I don't need to go back and forth between the Morton index and do things like that. So this is because I'm using this. I'm using the two-dimensional index to index the m. And the result that I call ui prime, I am numbering as L, the local expansion, because it makes more sense later on to call this a L, local expansion. Then the calculation of the distance is also very easy. If you have ix and jx, you just divide that by 4, and because your domain is divided, it's a 0 to 1 divided into 4 segments. If you divide by 4, then you get the actual distance by just from the two indices. This is the distance from the center of the two boxes, and it's very easy to calculate r as well. And then you just divide by r. So this whole code becomes much cleaner because I'm now using the two-dimensional index. And now the same for the L to P. I just need to search over loop over all the points. For each point, I find which box it has the effect from, and I use that center UI and substitute that into UI, or accumulate it into UI. And then this part is also neighbor finding, can be done very easily by using Ix and Iy again. So from each point's coordinate, I calculate Ix and Iy. Same for j, I calculate Jx and Jy. And then I do the opposite of what I did for the M2L. I see only the close ones. So if this is close, less than or equal to 1, and also this is less than to equal to 1, it's inside that near domain, 3 by 3 box. So then I do this calculation here. And just to avoid when r is 0, I have this if r is not 0 thing. And then I just add to UI. And then checking the answer, I have something almost equal, except this is for everything against everything. I don't choose the near or far. I just do it for everything. And then I compare the answer UI against what I calculate here UI. And since UI is initialized here and I'm still inside the I loop, I don't have to put it inside an array. This UI I just can directly compare with this UI, and it should be the same. Well, it should be close. And so now when I actually execute this code, I actually get quite accurate answers, you will see. So step 2 was the code that I was just looking at, and it had n equals 10. So I'm still using n equals 10 for step 2 as well. So it only shows 10 numbers. But you can see that the two numbers I'm comparing, the one I calculated with the near and far approximation and the one I calculated directly, are quite similar actually. So now you know that this code is working for this kind of calculation. So now I cleaned up the code, so if you go back and review what step 2 was, now it looks exactly like this picture. So this is what I actually wanted to do. And so now, from here, it's only small changes. So once we have something that is doing the proper FMM, it's a single level FMM, but still it's doing something that is almost the same as a proper FMM code. And then I introduce in step 3 the Morton index that we discussed. So how to change this two-dimensional numbering into a one index. And then I do this very incrementally. So say, I'll show you by opening step 2 on this side. So I'll open step 2 on this side, and then I will open step 3 on this side and show that they are almost the same code, except for this get index and get ix that we defined yesterday. So here I am introducing some new things, but this is what we did yesterday, except I cleaned up the code again a little bit more so that it makes more sense to me. I don't know if it makes more sense to you, but now I am explicitly looping over JX. This is instruction that says look at the first bit in your number, the bit at the least significant digit in your integer, and shift that 2L times, which means you're taking 2 times L power of that number. And basically this is doing the same thing as yesterday. It's taking in Ix and then returning the index. Yesterday we had that as a parameter here, but it makes more sense to just return the value. So you can do something equals get index, and this something will have this value as the index. And same with get Ix. I cleaned up the code so it makes more sense to me. I don't know if it makes more sense to you now more than yesterday, but to me this is easier to understand. So it's basically taking index. Now I am sort of shifting index, decreasing its value, but extracting the bit by bit and putting it into both Ix and Ix0 and Ix1. So it's sort of doing the opposite of this thing. It's instead of putting numbers into index, it's taking numbers out of index and putting them in Ix and ix0 and ix1. So this is the same function we had yesterday, just a little bit cleaner. Now compare the two sides of the codes I'm looking at. So it's almost the same here. I think it's identical here actually. And then when you go down here, so remember, by having this two-dimensional index, I was able to make the code very clean. But now I'm going to introduce the Morton index and see if the code can still remain clean. And by introducing a Morton index, now this two-dimensional ix, iy turns into one index I, and jx, jy turns into the same index. So let's go down a few lines and see what this looks like in both codes. So initialization, so P to M, let's bring P to M up a little bit in both sides. Okay, now we're looking at P to M on both sides now. Now, before, from ix, iy, I'm directly addressing M. But instead of directly addressing, I put that into the ix0 and ix1, and then I just add one function call, getIndex. And now I can index this with this Morton index instead of the two indices. It's just one addition. So the code is not more complicated or anything. Also, now I can change these ix and iy loops, jx and jy loops, into just two loops. So instead of 4 loops, I have 2 loops. Except I need to change this one number I into two numbers, ix0 and ix1, and this one number j into jx0 and jx1. And then I do the same thing I'm doing for ix and jx because they essentially mean the same thing now. So I don't change any of the code structure here. I just use a different, every time I need ix and iy, I just call get ix. And every time I want to get the one index, I and j, from ix and jx, I just call this function here. So I'm adding a little bit more functions, but it's not, the change is small when you just compare step 2 and step 3. So I think you can follow quite easily the logic on both sides. Same for L2P. I just add one line that says get index so that I can reference L with one number. And also for P2P, I don't really need to change the index to one index. I can just keep using ix and jx because I don't use the Morton index for the direct part, and I don't use the Morton index to check the answer. So this part is also the same as before. And just to check that the answer is correct, I will show you that the answer is correct by just let's see. Oh. By executing step 3, now I just added Morton index, the concept of Morton indexing, so the answer shouldn't change. But now, this is gradually, so the reason why I introduced Morton index when everything was working perfectly fine is because as we progress, and also today when I described to you the adoptive FMM, you need to have the Morton index working. So I have to introduce it at some point. And introducing it here, I thought was the easiest increment in terms of gradually getting to the full FMM code. So now in step 4, what happens is I introduce a deeper level, because right now what I'm doing is only level 2 calculation. So it looks just like this. I'm just doing this calculation. But instead of becoming suddenly multi-level and introducing the M2M and L2L and all the concepts of how to find the M2L interaction list in a multi-level tree. I don't want to do that yet, but I still want to do a deeper level. So what I decided to do was something like this. So I divide the boxes further, but I just do the near field and far field at a single level. So the resulting code is going to do something like this. Slightly inefficient, but it's good as a sort of midpoint before suddenly going to multi-level. So this is single level, but at level 3. So this is level 3. And let me show you how similar the code is when you compare to, so I think on this side I am looking at step 3, and on this side I am looking at step 4 now. So it's identical here. I still use the Morton index, so I have these get index and get ix functions, and I have these on both sides. Also here is completely identical, so I'm gonna just skip this part. Okay, I introduced something slightly new here where I calculate, so before it was 16 because I knew it was level 2. I knew I was going to have 16 numbers. But now I made this into a variable. So nx is the number of boxes in one direction. So if the level was 2, then this would be, nx would be 4. So you'd have 4 by 4 boxes in total. So that's 16. Now if you increase the level, then this would become, say that this was 3, then nx would be 8. So this would be 8 by 8, and n cell would be 64. So in this code, I am actually setting level to 3, so n cell is 64. And then I loop over 64, but the difference between this code is this one is just hard-coded to 16, whereas this one you can change to any level, and it would still work. And so the P to M doesn't really change because you need to loop over all the points in the domain anyway. And note that most of the boxes are empty here, and this code is still working. So it's automatically skipping over the empty boxes. And so I'm initializing m to 0 here for all the 64 boxes, but I'm only adding a value q to the ones where the j has a particle. So only if if this loop covers, only if you have a body inside that cell, this gets added to that box. So basically I am skipping over all the empty boxes in this loop, the P to M loop. But it doesn't harm the execution of the code because whenever I'm executing the M2L part and referencing M, the ones that have empty, no bodies, the M is 0. So it's as if I'm ignoring it, but I'm actually calculating with 0 here for now because I'm not skipping anything in the M2L at the moment. So here, again, this is looping over 16, but now this has changed to n cell. And so before, in the picture that I was showing in the keynote slide here, before it was going from 0 to 3 and 0 to 3, and then it was separating the near and far by doing the if statement shown here. So if absolute ix0 minus jx0 is larger than 1, this means it's far enough. So notice that I'm using the same number here. So this is what will produce an interaction list that looks like this. Because I'm using, if it's larger than 1, that means everything here. Because I'm not looping over the parents, neighbors, child's non-neighbors. I am actually looping here over everything, all the n cells. So I'm looping over all the cells, and I'm just saying, if it's further than, if it's not your neighbor, do this calculation. So it will do all the calculations for all the boxes that are far away, in like the picture I showed you. But still, it's good because it's good to have this intermediate step 4 because it's easy to code. L to P has also not changed. So, and P to P doesn't change. So basically you have, the same for P to P, and check answer, it also didn't change. So when I execute this code, step 4, you will see that so the numbers are larger than before, but they're still matching quite well. The numbers are larger because I increased the total number of points to 100. Before it was 10. Now I use 100 points and level 3. But so now this code is working for a larger number of points. And you can see that the answer is still matching quite well. And so that this is step 4. Step 4 was, if you view it in a picture, step 4 does this. Now, step 5, finally, we introduce the multi-level. And so going from level 3, single level, which was step 4, to level 3 and 2, multi-level, is not so much of a difference. So I will show you how similar step 4 and step 5 are. And so now it's easier, I think, for you to follow because I'm looking at codes that are quite similar. So again, this is step 5, multi-level. This one is single level at level 3. And up to here, you can see that it's identical. So it's good to do this kind of exercise where you're looking at code that doesn't change too much. Again, so here, I changed n to 100 in the last case, so it remains 100 here. And level 3 is the deepest level. So when I do multi-level, now I don't have to change these numbers because this one was already deep enough to do multi-level, but I just did it with single level as an intermediate step. And so now this part doesn't have to change when I go to multi-level. And then if we go down further on both sides, you can see that it's still almost identical. So I introduced the concept of nx and ncell, and this is 64. And this is the same, but now I introduce one thing. So this is the one new thing I introduced in step 5 is, so m was only at the bottom level here. So I just had to have n cells at the bottom level. Now I have 2 levels or more levels in the tree to look at. So of course at the bottom I have n cells, but I actually made this into a 2-dimensional array which takes into account from level 0 to level 3. So because it starts from 0, I have to add 1 because it's 0, 1, 2, 3. So there's 4 numbers in there. And so level is 3, but it starts from 0. So I have 4 levels that I can store m, and I have 4 levels that I can store L. I don't actually use all of it, but again, for the same reason that it was useful to have the ix and iy referencing the m in the beginning, it's easier to code when you have like this way of indexing m by the level, and then also where inside that level you are. So it's like a two indexing of the multiple expansion and local expansion. And then I just loop over all the levels and all the cells and initialize the values to zeros. So at the higher levels, or like the smaller levels, I should say, the n cell decreases because as you go up the tree, the number of cells in that level decrease 1/4 and then 1/4. So I don't need to have this large array at each level, but it's easier to code, so I'm just using a lot of unnecessary memory for now. And later I will try to reduce this. But it's always nice to have an intermediate code which does something inefficient in terms of memory just for debugging purposes. So I'm introducing level here. Level means level 3 because level is set to 3. Inside the loops, I will use the letter L to express the varying levels. So L is a counter that can change from the deepest level 3 to any number. But in this case, I'm just looping over all the levels. So now the difference here is step 4 was single level, so it didn't have the M to M step that goes up the level. But now I have a loop that goes from the bottom to the top. This is going up, so the L is decreasing in this case. And then NX and NCell are dependent on the level, so I need to recalculate them every time the level changes. And then I use this parent level, which is L minus 1, and I divided by 4, as we learned yesterday, that the Morton index, if you divide by 4, it becomes your parent's index. So this is your parent's level and parent's index, and this is your current level and your current index. So the coding is very easy. I don't have to do that level offset thing I did yesterday. I just need to put one number here and one number here that tells you the level. So again, this is just for making the code easier, and so that the difference is small when I go from step 4 to step 5. Again, here, M2L was happening only at the bottom level in this case, so I didn't have to do too much. But now I have to go through all the levels. At level 1 and level 0, the M2L interaction does not happen because all boxes are next to each other, or either, at the top it's the same box. So at level 2, M2L can happen. So, and then you just go down the tree. And for each level, you have to recalculate the NX and NCell, and then loop over. I'm doing the same thing I did here. I'm doing this inefficient thing by looping over all the cells. And then here, I identified only what was far. You see, so in the picture that I showed you in the slide, before, I was only saying what is far. So there was only one if condition that says, if it's far, I just do it. So the red boxes are, all over the far domain. But now, I have two conditions. So see that I've changed the conditions to, this one says it's far, larger than 1. So I still have the same condition, larger than 1, if it's far. But also, notice that I've added another condition that examines if it's close enough. So this loop here, it's kind of hard to show in one line, but this is looking at the parent's IX index. So again, remember that you can do integer division by 2 to get not just for the Morton index, but also for this two-dimensional index, IX 0 and JX 0. If you divide that by 2, you actually get your parent's IX 0 and your parent's JX 0. So this is looking at the parent's two-dimensional index and saying if that's neighboring. So you remember the condition was your parents' neighbors' children that are not neighbors. So this is actually looking at the parents' neighbors. This if loop is looking at if the parents are neighboring. And then this loop is looking at if it's not your neighbor in your current level. So these two loops actually allow you to form something that looks like these two. So this thing. So it's looking at your parent's neighbor, so it excludes all these white boxes here. It restricts you to this domain. And the other if condition says it's not your neighbor, gets rid of all this white space. So now you have this red part being defined without doing any of the Morton index manipulation. You just have to do loop over all the cells and then try to find the ones that are in that red domain that's not too far and not too near. And so this part, the inside, doesn't change. I just have more levels, looping over all the levels, and having this near and far condition, both near and far condition. So that's the only difference. And also, I only had one level here, but now I have this L as an index, the level, to identify which level I am looking at. So now it's much easier to understand the progress. I've introduced very simple concepts without, like in yesterday's live session, I went back and forth because I had to introduce like level offsets and how to deal with this neighbor finding, going back between the Morton index and the 2D index. It became very complicated. So I decided to make things simpler by first doing this version, level 3 single level, and then the multi-level, so that the difference is very observable. You can very easily see that there is not too much change in the logic of the code. And now, once you have the M2L, so going down the tree with the L2L expansion, also the same. You introduce the concept of levels, you recalculate NX and the number of cells in that level, and then you loop over all the cells in that level, and then for the empty cells, again, the number in here it would be 0. So it's as if you're not doing the calculation, but it's okay. I'm doing all the calculations and calculating all the zeros in this case. And again, the parent index is I divided by 4. The parent level is L minus 1, and your current level is L. Your current index is I. And it's very simple logic that I showed in the slides, and the code is following very closely what I've written in the slides this time. And then finally, you're at the bottom level again. So this level thing means the maximum level 3. And then you recalculate NX and N cell. You loop over all the points, and you insert the bottom level L with the index J that you get from the get index. So I'm still using the concept of Morton index here, but not too much. Only in places where it doesn't complicate the code. And then you get UI, and the P2P and the check answer part, as you will see, do not change. So the P2P check answer, so you can compare the two codes. These parts don't change at all. They're identical. So introducing multi-level doesn't change these parts. Okay, so now let's see if step 5 will give the correct answer. So it should give something similar to step 4, because I'm using the same 100 particles and then 3 levels. So it's conceptually doing something similar, except the difference is very easy to see in the picture. So this one was doing this picture, and now I am doing this picture. So what I changed is very easy to see in the slides now. I only changed that thing, so the answer shouldn't change too much. Okay, so now, finally, this is the last slide for the code review. I introduced the concept of level offset here, finally. So remember, I was using the level as the index in step 5. So step 5 had Step 5 was using the level to index. Now, when I open step 6, you will see that I no longer have a two-dimensional index. So if I go down to the part that's different. Okay, so now I don't have the 2D index. Now it's 1D index again. But I had to introduce another concept, which is, I did this yesterday, but I sort of did it along with too many things, so I think people got confused. Now I'm only introducing this one thing here. This is the only new thing in step 6. So step 5 didn't have this level offset, so it had to use an index. And it takes up a lot of unnecessary storage because, as I mentioned, all the levels don't need n cell dimensions. So you don't need a level plus 1 times n cell memory storage. You can compress that a lot. So by using the level offset, you can compress the storage. And what you're doing is you're basically doing what's shown in this slide here. So instead of using 0 and then 0, 1, 2, 3, and then starting from 0 again, the Morton index starts from 0 at every level. So you're actually using an offset. So you offset the 0, 1, 2, 3 by 1, and then you get 1, 2, 3, 4. You offset 0, 1, 2, 3, 4 by 5 in this level, and then you get 5, 6, 7, 8. So it's sort of contiguous from the top, 0, 1, 2, 3, 4, and then 5, 6. So the whole tree contains a unique index by using this level offset. This level offset is just a concept of making the index, the Morton index, sort of a unique between all the levels. And this number on this far left side is the level offset. So it's 0 at level 0, 1 at level 1, 5 at level 2, and 21 at level 3. And so that is what's being calculated here. I'm looping over and I'm just adding to the previous level offset. And what I'm adding, I think you can see if I move over here, I'm actually adding the number, the total number of boxes in that level is, it's like 4 to the power of L. And this is how you can calculate 4 to the power of L using bit shift operations. So now, everything that I've used, the L, now I need to change to this n cell plus level offset. Well, this is initialization, so I need to initialize all the boxes. So it's n cell plus the level offset is the maximum size of M and L. And now, every time I index, before I was using level J. Now I use J plus level offset level. So all the places where I've used J level, I'm using J plus level offset level. And if you keep going down, you'll see this same change happen again and again. So it's almost, you can do this very blindly without thinking too much about the change, because every time you have J level, it's J plus level offset. So you see here, I divided by 4, L minus 1, it's I divided by 4 plus level offset L minus 1. So it's like a very systematic change. Now, yeah, it's I plus level, you can't see, but you can already guess what's here. Level offset L, right? So you can very easily change your code, and it's very difficult to introduce bugs if you're changing very systematically like this, because the changes are very obvious to you. It's I plus level offset L, because Li, and then this also changes to J plus level offset L. And so those are the only changes. You don't need to change anything else. You just need to change the indexing of L to this I plus level offset L. And then you're actually very close now to where we left off yesterday. And yesterday we actually sort of didn't finish the M2L. We stopped here. So we didn't do the L2L and the L2P in yesterday's hands-on. But today we can progress quite easily because, well, first of all, I'm not coding live, and also because I'm gradually introducing the concepts of, for example, level offset. So again, I plus level offset L, because this was L and I. And so the change is very minimal, and of course P2P and check answer, again, are completely identical in this case because it's not affected by the level offset. And so now let's try to execute step 4. Oh no, step 6. Okay, so it shouldn't change. I just introduced the concept of level offset. And algorithmically, it's identical to the previous one. It's still doing this calculation, except whenever it's using much less memory now, because instead of storing like a entire square array that has n cell times the level, now I'm storing very few at the top and only n cell at the bottom. And now, finally, step 7 is the code itself is unfinished, so I haven't completely finished introducing the concept, but I've added the part where I do sort the bodies and get this array. So maybe you can continue from this hands-on and try to finish introducing the benefits of sorting the bodies. So until now, step 6, we have not really sorted anything. So yesterday I also introduced the concept of sorting at the same time as everything, so it got very confusing. So I decided to separate the introduction of the concept of sorting until step 7. So here, again, everything is identical. And between here and the main function, I introduce a sorting function. So here I introduce this thing called bucket sort, which is slightly different from what I showed you yesterday, radix sort. But in terms of code, it's much fewer lines. Yesterday I had many for loops because it was a radix sort. But bucket sort, I think some of you know how bucket sort works. It puts the numbers into like a bin. So it's like a binning technique. And then it counts how many points are in that bin. And that count is actually the new index. So if you incrementally sort of count per bin, and it's also like using the concept of offsets, and you can actually get the new index in order n. You don't have to compare numbers to sort them. This is not a comparison sort. It's actually a counting type sort. So anyway, this is just sorting the numbers x and y. So I introduce the Morton index is the input. This index thing is the Morton index. And then I take in x and y, and I do the sorting of x and y inside this sorting function. So instead of using like the permutation thing I tried to use yesterday, I don't need that here. I'm actually directly permuting x and y inside this sorting function. So once I call bucket sort, x and y get sorted. So the difference between the two codes now is that before I do the P to M, so I first define x, y, u, q in the same way that I do here. And before I calculate the M, or even before I initialize the M and L, I calculate first the Morton index. So get index, if you pass in ix and iy, which is calculated from x and y times the number of boxes in each direction, then you get a unique index, a two-dimensional unique index, and then you use that to turn that into a Morton index. And then I'm printing the Morton index here before the sorting. And then I call bucket sort, and it takes in input values x and y. It sorts them according to the Morton index and then outputs a new x and y. And so if I call again the ix, iy, and then calculate the Morton index again here, then if I print, the Morton index should be in order, and x, y should be the corresponding coordinates. So I've changed only up to here. I haven't touched the code below from step 6. So from step 6, from here downwards, it's the same code as step 6, but I've only introduced this sorting part, and I haven't really done anything with it. But even from just this printing, I can show you that step 7 should give you, if I need to go up further. So this is before the sorting. So see that the numbers start from, you're not seeing the left end of my screen. So this is the index of the loop. And you see that the index of the cells, the Morton index, is completely random. And the x and y coordinates are also completely random. order. And then now, after I reach 100, so this is after the sorting. You see that the Morton index is sorted. It's jumping because, for example, cell number 3 and 4 don't have any bodies in them, don't have any particles inside. Also, 10 doesn't have anything. 9 has 3 entries. So you can see that the Morton index has been sorted, and the x and y have been also moved to correspond to this. Now, the task is to create the offset so that you can index, for example, if you just had this offset for this index here, 11, and the next offset for 14, I could access all these 3 numbers with just that offset. So what I want is, when given number 9, I want to retrieve the x and y that have the Morton index 9. So when I give I want to make a function where if I give it 9, it will return me a loop counter of 3 and then loop over x and y starting from index number 11 so that I can index these 3. And then I can use that in the P2P function, I can use that in the P2M and L2P, anything that involves a P. I need to index the particles. So I can use this. But I haven't coded that yet, so maybe I will do that maybe today and show that to you at some point tomorrow so that you can review. But anyway, so this was my sort of refreshing of the code so that it became a little bit confusing yesterday, so I thought that was not good. So I decided to refresh everything, and on the website it's all refreshed. So if you go to the Google Drive from this link here, if you click this link, and then it will show you all the new code, step 1, 3, 4, 5, 6, and 7. And the codes I just discussed are already up online. So in case you were confused yesterday about the code, now I've cleaned the code and checked that there are no bugs, and started from the very basic and gradually went from step 1, step 2, 3, Morton index, 4 single level at level 3, step 5 multi-level, step 6 level offset, and step 7 sort bodies. And after you finish up to step 7, I think you have pretty much a fairly reasonably sophisticated FMM code. And now, after that, you can start to introduce the high order expansions, but that's a little bit more mathematical. So I won't do that in the hands-on, but I can give you the functions you need to call in terms of the code. So maybe I'll call that step 9 or 10 or something. So up to now, we are able to construct a somewhat uniform tree and do all the calculations. Next, in the next 50 minutes, I will introduce the concept of adoptive tree structure. So until now, we were just looping over all the boxes everywhere. And in case the particles didn't exist in a box, it was calculated as a 0 entry. It was still calculated though. So it wasn't skipping the empty boxes in that sense. In the next 50 minutes, I will introduce what happens if you have a tree that looks like this, which comes from particle distributions that could look like this, or just on the surface of a sphere. You have these in actual scientific calculations, so you need to know how to change your code so that you can accompany these special cases. So this is going to be the next 50 minutes. So we will have maybe 10-minute break and then start with the adoptive tree. Okay, thank you. Okay. Okay, so today we will discuss a little bit about when you have non-uniform distribution of points, you need a special tree structure to handle the empty parts of the space. And so we have discussed somewhat the tree structure that looks like this, the uniform tree. But when you have distributions that have a lot of empty spaces and also high concentration, high density of particles in a particular part of your domain, then you need to divide that dense region deeper. So then you have a deeper region of the tree, but other parts remain shallow. And so Plummer distribution is something that physicists use sometimes in their test calculations. And you have a non-uniform distribution, but it's still that if you plot the depth of the tree with the number of points, then it still has a log. It's 3D, so it's base 8 log, but you have a log n behavior in the depth of the tree. So any tree structure, so if it's completely uniform, it's exactly base 8 log of n. This is your exact depth of your tree, if it's a full tree. But if it's a non-uniform tree that is somewhat of a reasonable non-uniformity, then it's always a constant plus that 8 base log of n. And it's never like this, where, so think of a case where your tree is branching at every level and you have one branch that is always empty at every level, and then it keeps getting deeper and deeper. So for n points, you could potentially have a depth n tree. It's possible to construct a tree like this. But think of what that means. So this is not a very realistic tree structure that would happen in any scientific calculation. The reason is because the criteria for dividing the tree is basically the density of your points in that box. So what you're saying here is each of these points have equal density and are divided, like in the center of the box. So at the top, you're dividing in half, and this side has very few points. And then this side has very few points, this side has very few points. But you're subdividing into smaller and smaller boxes exponentially. So what this means is if your distance between all your points was exponentially decreasing at some location in your domain, then yes, this might happen. But in any calculation, you don't put n points in your domain with exponentially decreasing distance, like your delta x, the distance between 2 points, being like orders of magnitude much, much smaller than any other point is not typically a distribution that happens in any computation. So excuse me. This doesn't really happen in the actual case, but this does. So we need to know how to deal with this kind of tree structure. And so there are a few concepts that I've already introduced that will help you with the adoptive tree distribution. So let's say the tree had this kind of structure because the points were distributed densely in these areas, but the space was empty here and here. Let's say we had this kind of distribution. It's reasonable distribution to have. And in this case, so looking back at the Morton index, there's something we need to remember. So when we have only non-empty boxes that are spaced like this, it's very tempting to number them like 0, 1, 2, 3, 4, 5, and 6, 7, and 8, and then reference the boxes according to that. But then this number is no longer the Morton indexing. And what happens is you can no longer do this. You can't change this number 14 into 2 and 3 because number 14 would mean something different. It says 7 here. It used to be 14. And this turns into 2 and 3, the two-dimensional index. But if you number them like this, then you can't retrieve the two-dimensional index anymore. So you have to keep this numbering, but skip the numbers. And so basically you need something that computer scientists would call a map, or like a hash table. So these large numbers that are skipping are your hash keys, or some large. This number itself could be large and not continuous, but you can have some function that maps this numbering, 0, 1, 2, the continuous numbering, to these numbers here, so that you can have an arrow mapping back and forth between 15 and 8. In the same way that you're mapping between these two-dimensional index and one-dimensional index, you can have another map between these two numbers. And it's typical in adaptive fast multiple method code to actually have such a map. So you loop over this index that goes 0, 1, 2, 3, 4, 5, 6, 7, and 8. But to get this box in the tree, you actually put it into a function that is like a map between the number here and number here. And you can create this very easily in the beginning of your code. And maybe I will actually do this in a hands-on session today, that once you have the index that is jumping like this, and I do have this in step 7 in the code right now. And so actually I was preparing step 7 so that we can practice what I am going to explain now. I can actually loop over these indices and have a counter that is incremented every time the number changes. So if you number all the particles according to this Morton index, then you'd have 0, 0, 1, 1, 1, 3, 3, 3. And so every time the number is the same, it's still in the same box. But then whenever it changes, you need to increment this counter. And then you have a loop that has a counter that goes 0, and then 1, and 2, and 3, every time it hits a new box. And then you are also keeping this index, the Morton index. So you can actually, you have these two numbers inside your loop that you can associate to each other. So you can create an array that indexes this and say that equals this number here. All you need to do is create such a loop, and then you have the map. You can have it both ways. You can say one array that has a bunch of zeros here. When you input 8 to that array, it returns a 3. And if you input that to that array, if you input 7, it returns, like -1 or something that indicates that nothing exists there. And to map forward, it's very easy. You just need to keep this counter. When you index by that counter, you make it equal to this number here. So you create two arrays that map both ways, one in this direction and one in this direction. And when you're mapping in this direction, you have some entries. You can try to input Morton key number 7, and you need to be able to tell this map function that nothing exists here. And typically people use like a negative number to indicate, like -1, to indicate that it doesn't map to anything in the tree. So once you have this map, it's very easy to start skipping the empty cells. So in the code I showed this morning, I was always looping over everything from 0 to n cells, which was like 15 in the loops. Now we only have to loop, because once you form this map in the beginning, you actually know exactly how many non-empty boxes there are at each level. So you can just keep this number and make all your P to M loops and P to P loops for just these non-empty boxes. Also M to L. All of these operations don't have to loop over from 0 all the way to 15. You can just loop over the non-empty ones. And for adoptive tree, then you can save a lot of memory also by having this map, because all the cell, once you start storing multiple expansions that have many numbers in them, which you do in the actual FMM code, then if you have to store zeros just because you didn't want to skip the empty boxes, then you're storing a lot of zeros in the multiple expansions that don't represent anything. So if you can somehow delete those from your memory space, then it's very memory efficient. And so when you number according to the Morton index, all you need to do is create a map, not so different from the one we created with the 2-dimension to 1-dimension. And then you can still index, because you have something that looks like this now, with a lot of empty spaces, but every time you get number 7, you map that to 14, and then 14 maps to 2 and 3, and then you can do whatever operation you want to do. So there's 2 steps before you can actually find your neighbors or do the M2L interaction list finding, but then you know that it's possible. So yeah.
Sorry, so I'm trying to imagine that say if there's some particle keep moving, then the distribution of particles are actually keep changing.
Yes.
Then in that case, does that mean my adaptive tree will be just keep changing?
Yes. Yes. So well, that's actually a very interesting question when you're doing like MPI calculations, because to reconstruct the tree locally on your machine that doesn't, is not connected to other nodes is fairly fast, because access to memory is quite fast, and you can just reconstruct another shape of the adoptive tree. You can just do it from scratch. But then the problem is when you're doing like an MPI calculation on a supercomputer and this part is on a different node that's far away, then when the structure changes far away, that information needs to arrive to your node. And to do everything completely from scratch in that case is not very efficient. So you need something like an updating scheme. So a tree that can gradually change, because particles don't suddenly move from here to here. They move like in delta t, they move very slowly. So it's like this tree will gradually change. This branch that says 013 might change to 012 like this. And these branches might wiggle like this. But sometimes this will jump to this branch here. So this kind of jump is the one that requires some consideration. But otherwise, like incrementally updating your adaptive tree structure is still an open area of research. So there's a lot of careful ways to minimize communication during the update, and also do it in sort of a bottom-up way that doesn't require any global communication. That's sort of like a local propagation of load balancing. And so that also leads to many questions for how to load balance again. So I'll discuss some of that in maybe tomorrow's lecture, but for today you just have to know that there are some adaptiveness to the structure. And also this is also related to when you go to very, very large calculations, then there's actually a limit to how deep the tree can be. At first you may not notice this, but if you think about it, you'll understand that. So say all these boxes represent a bit. So an integer in a C code is 32 bits. So you have, if it's an unsigned integer, you have the signed part. You can also use the signed part. So you have maybe 10 levels to store, if you're in 3D, XYZ, XYZ, XYZ. So you have 3 times 10 bits to use before you hit the limit. What happens after this? So if you wanted to go to level 11, you can no longer express the Morton index with an integer. It will overflow. So when you have a uniform tree, level 10 would mean like a very, very large n. But if you have a non-uniform tree, then one branch could get very deep. And the problem is you need to index with that number somehow. So that's the difficult thing. So you remember, when you create this kind of map, you still need something that takes in the value 15 and returns 8. So when this number becomes 10 when this branch goes down to the 10th level or 11th level, this number becomes huge, and you can no longer index an array with that huge number anymore. So that's one of the first limits you will hit, is when you want to index a box with a Morton index, then you hit the limit very easily. So even if your integer has not overflowed, so say that you used a long, this is like a 64-bit integer. So a long integer, if you use a 64 bits, then again, it's like double the number of bits. So you can go maybe to 21 levels, because here you're sort of not using these two, but if you had 4 more, you can fit another one in, which is the 21st level. Then, but still, when you are able to do 21 levels, your index has not overflowed, but there is no way you can index something with a number so large. Basically, to handle index of 64 bits, your memory space has to be 18 exabytes. So if some of you may remember back when we had 32-bit operating systems, even if in your motherboard, if you put more than 4 gigabytes, the Windows wouldn't recognize the 4 gigabytes. It's because of this issue here, actually. Even if you had memory that's huge, the thing that's indexing that memory, because the pointers to the address are actually written in 32 bits in a 32-bit operating system. So you need to have much more space to address your memory. Even if you had enough storage, you wouldn't be able to access it because of the integer overflowing. So now we have 64-bit operating systems. So if you can somehow fit this many bytes of memory into your machine, then you can actually address that. But the problem is, when you're talking about indexing arrays, you don't want to create an array of size 4 gigabytes just because you want to access the array, the Morton index at the 10th level. And if you want to know how large the largest calculations in FMM are, they're a bit larger than 21 levels. They're like 23 levels. So how are these people using these indices? So this index has overflowed. There's no way you can create an array that fits all those numbers. You would need 18 exabytes to store such a thing. So how do they do this? So this is how, when you map the number between 15 and 8, you don't actually access an array when you go to very, very large scales. So you actually create something like a hash table. Maybe those of you who don't know what a hash table is, so you don't treat 15 as a number. It's more like you treat it as some key value or a string or something that maps to a given value. So it's like a pair of values, and you map one from the other. You don't necessarily need to have enough space to index that large number in that case. It's just associating one number with another one without actually, using that as the key to the address space. So it's an efficient way. I mean, so in C++, there's actually a already prepared container called map, which if you input a huge number, it will still return. You can associate that to a small continuous index. And the easiest way, if you're coding in C++, is to just use that map function to input a Morton index and associate that to this continuous index. And then you don't have to worry about this issue of overflowing because it's not actually indexing with that number. So all you need to worry about is this overflowing of the 64-bit integer itself, which you can go all the way to level 21. So it's a lot better than the limitation of going to level 10, because on your local machine, you may have more than 4 gigabytes, and you may be able to access more than 10 levels. But think of what happens when you're running on a huge, huge supercomputer. The Morton key of the global tree, the entire big tree that's distributed, will easily exceed level 21. So you need to have, when you're thinking about adoptive trees, this is one of the things you need to consider, because the integer can only store so much. And the thing is, Morton index is not really something that you index an array with. It's more like a key value that you use, and you have to map it to an actual index that's smaller. So the reason why I talked about this map before talking about this issue was because this one is continuous, and it makes sense to actually index an array with these values. It doesn't make sense to index an array with these values. But in the hands-on session, like step 7 or 8, I will actually try to index an array with these values, because that's like an easy intermediate step. And then I'll introduce this map here in the same way that I introduced this map here later, and the code was cleaner when I was using a memory inefficient version of indexing. So there are multiple instances in the FMM code where the inefficient memory usage gives you a very clean code. And then when you start to worry about memory efficiency, the code gets uglier and uglier. So at some point, you need to really think, do I want my code to be so memory efficient, or do I want my code to be somewhat cleaner so that I can add more features and just use a machine that has more memory? And just, if I'm using MPI, it's going to be distributed anyway, so maybe I can not be so memory efficient and just distribute everything. So there are some considerations you need to make when designing your code. In the same way that I refactored my code to step 1 to step 7 yesterday, so that it gets much cleaner. So just because there are these issues doesn't mean you have to use advanced features to index your array or anything. I'm just stating this as a potential limitation of trying to index Morton indices. You try to use Morton indices for indexing small arrays. Okay, so now in an adoptive tree, this is something that we didn't have to consider in a full tree, because in a full tree, you knew that all the boxes were full, so you just wanted to consider, what is close and what is far. But when your tree has different depths in different areas, your interaction list needs to consider different levels, because, for example, consider this bottom of the tree case. So I explained that at the bottom of the tree, there's always a part where your neighbors need to be calculated directly. But say that your tree has different bottom levels. So if they were mismatching, what would this list look like? Because your neighbor is not at the bottom. Your box may be at the bottom of your branch, but when you look at your neighbor, the tree is actually getting much deeper. So then you need to consider something like this. So this one, the B, is the blue box that I is showing, the center box shown here. And so for this box, some of its neighbors go much deeper. So you need to go deeper in the interaction list. And you may be able to see, maybe not, but this is numbered from 1 to 4. So, or 1 to 5 actually. And it considers different types of interactions, but mostly one is similar to the P2P, and 4 and I guess 2 are similar to the M2L. And I think 5 is similar to this white part here, which you have to consider at some upper level of the tree. So and also 3 is similar to the M2L. But so in some cases, if you know that you have deeper areas in your neighbor, you actually need to consider that during the interaction list construction. And the most popular one has 4 types of lists, where one is the close ones that are at the same level or deeper than you. One is at the far boxes, but at the same level. Far boxes at deeper level, and far boxes at a higher level. So it wants to consider different strategies for this. And so if you construct something like this, then you can actually calculate the adoptive tree M2L and P2P interactions quite efficiently. Also, there are other types of interaction lists which sort of consider a larger neighbor domain. And if you do this in an adoptive tree, in 3D, it becomes very complicated. So say that you had to construct something that has a neighbor region that looks like this white region. So it's closer to a sphere than the other ones, so it's more optimal. But so if you had to construct something like this in a neighbor criteria that looks like this, things become very complicated in your code. So you need to really consider whether it's worth it or not. But fortunately, there is a nice algorithm to construct such interaction lists for adoptive trees. And so it's called the dual tree traversal. I mentioned this briefly in, I think it was yesterday's slides, when I was talking about the tree construction for the linked list, the interaction list construction for the linked list type tree. I mentioned that you can construct interaction lists not just for the index-based tree, but for the linked list type tree. And so this is the algorithm that does that. It's been cited, so originally, before FMM was first done by Greengard and Rocklin in 1987. But Apple had a paper in 1985 that introduced this concept itself. So it was an order n method to handle n-body problems. It just didn't have the proper error bounds, and it didn't introduce like the higher order expansions or the nice octree structure that is necessary for having these nice error bounds. So it was sort of a nice idea that appears on and on periodically. Warren and Salmon introduced this, and I don't think they called it the dual tree traversal at the time, but they introduced this in one of their papers, but didn't implement it. I think the first time it was implemented, it was 2002 by Walter Denin, and it's basically a traversal of the tree, of 2 trees, and it's like a recursive function call. So the traverse is being called for the children here and here, and also here and here. And so it's like a recursive function call. And inside the recursive function call, this approximate is like the M2L kernel, and direct is like the P2P kernel. So you're choosing the near and far decomposition again, but the criteria for choosing the near and far is up to you. So in this case, it's written, so the first thing you do is you consider this MAC is the multiple acceptance criteria function, which is like a user-defined function to see if it's close enough or far enough. If it's far enough, so you can define the definition of far or near. So this is why it's so flexible. So you can define whether it's far or near with this kind of criteria or this kind of criteria, that's something that's closer to a sphere, or you can define it to be like a 5 by 5 by 5 structure. All these things you can, it's user defined in this function here. So you can use this first criteria to determine, so if it's far enough, you actually perform the approximation, the M2L calculation here at this point. And otherwise, you have the following choices to make. So first, if both of them are leaves, so this doesn't say if they're at the same level or not. So if it's a full tree, they will obviously be at the same level because all the leaves are at the same level. But if it's an adoptive tree that has different bottom levels of the tree, then this if statement permits that. So you can actually have different level leaf cells, and this will detect those. If both are leaf, it doesn't matter if they're at different levels. Then if they're both leaves, do the P2P kernel calculation. Otherwise means that either they're not both leaves. So if they're both leaves, it would be executing this one already. So if it's not this, then it means either both of them are not leaves or either of them are leaves. So one of them must be non-leaf. So if one of them is a leaf, the other must be a non-leaf. So you can divide it. So you loop over for B's children. You recursively call this function now for the children. Otherwise, if the other side is a leaf, the other side must be a non-leaf. So that means you can divide it further, and so you continue to traverse. Otherwise, if they're the same box, this might happen as well. If they're the same, then you can actually divide both of them at the because by the time you reach here, that means both of them are not leaves. So all of these cases means cases for the case where they're both not leaves. If they're the same cell, you can divide them both. And if one is bigger than the other, you always divide the bigger one. So if the radius of B is bigger than radius of A, and also this definition of radius, you can define by yourself. So you can define it as, let's use this as an example. So if you don't have a square cell, you can define it as the distance between the center and the corner, which is like the maximum distance. Or if you have something that looks like this, you can also define it from like the center or the average coordinate of the points to something that's the furthest from you. So, or if you have something that's like a hierarchy of molecular structures like this, you can define boxes to be like groups of molecules, and so that you don't split the molecules. And then you can define the distance as the size of the molecule. So it's up to you to define what this radius means. But in any case, this is a very sort of abstract algorithm which doesn't talk about the details. It just says, however you define the radius, if one of them is larger, then split that one. And if the other one is larger, split that one. So if A is larger, then it arrives to this and splits that one. So it's a very flexible algorithm because you can define what far and near are. The leaves don't have to be at the same level, and none of these interactions force you to interact at the same level, which means it will automatically detect all of these interactions at the different levels. So it will automatically create something that resembles this for an adoptive tree. So you don't need to go through writing a code, because typically if you write the code for finding the interaction list for these in this type of optimized interaction distance, then your code becomes very complicated, and you have a hard time when you want to take it to like a distributed memory. So you want to have a simple algorithm that describes this, and I think this one is a very simple algorithm for doing that. I don't have a code for this in the hands-on session, but maybe at some point in like step 10 or something we can swap the M2L neighbor finding with this kind of algorithm and see if it still works, because potentially it should work for any case. Okay, so now, since we are describing the interaction list size, I thought I'd touch upon subject of, so how to control the error is, there are two ways to control the error in the FMM. And I haven't really talked too much about controlling the error, and so you may still be wondering, how can I make the FMM more accurate? So one way is to, so there's a value theta that's sort of, it's called the opening angle. I described it earlier in the slides. It's like the angle looking at from here to the box size. So how small the boxes should be is like a function of this angle. So if you make the angle small, then the boxes would get smaller and smaller. But the closer ones are smaller because it's an angle. And so this angle theta you can control. And actually, we talked about the Taylor expansion in the first day. But this theta is actually what is being expanded. If you reformulate that Taylor expansion I showed earlier, you can actually write it as a function of this theta. And it's exactly this Taylor expansion of this function. If you look up the Taylor expansion of this function, it will tell you that it's this. So if you think about what this is, you can see that if theta is smaller than 1, this converges. And as theta gets smaller and smaller, the leading order term in the expansion is of the order theta to the pth power, right? So you can increase, so we are assuming that theta is smaller than 1 already. So it's a matter of how much smaller we can make it. So decreasing theta, which means the angle is decreasing, so the number of boxes that you interacted with will increase. So the amount of computation will increase because the number of boxes increases if you decrease theta. Okay, but the accuracy increases because it becomes a power of a smaller number. Okay, but then there's another way to increase the accuracy. You just need to increase p. In this case, the number of boxes doesn't increase, but what you do between the two boxes once you find the pair in this M2L calculation or M2M or L2L calculation, this number increases. So because you are using more terms in the expansion, you have to do a very heavy calculation between the two boxes. Like I mentioned, maybe I can actually show you the slide again just to refresh your memory, that the equation which you need to calculate given a pair of boxes is like this. So if you increase p, then you have to do many more loops for here, here, and here, because n increases when you increase p. So you increase all the calculation load of all these kernels. And typically, as I showed somewhere in this slide, that M2L, this part is the most expensive, so the yellow part is the most expensive part of the calculation. So if you increase the amount of calculation of this M2L part by increasing p, then your calculation becomes expensive. But that's the cost of increased accuracy. So it doesn't come for free. The accuracy is controllable, but it comes at a price. So then the question is, how much does the computation increase when you increase p? So if you look at this equation here, this is the expensive part, so we can focus on this. This is actually a loop over n and k. But so remember that n and k are both vectors. So if you actually write the code for this, you have 3 loops for n, nx, ny, and nz, because these have the 3 directions. And k is also a vector, so you have kx, ky, and kz. So you have 6 loops that loop over sort of as a function of p. So it's p to the 6th power. So you have a lot of loops. Now, there are other more advanced mathematical techniques which will lower the interaction count to like p to the 4th or p to the 3rd power. And maybe I have some, here. So these are so Cartesian Taylor is the one I explained in the beginning. It's a Taylor expansion, and it has Cartesian coordinates. You can use Chebyshev expansion. It doesn't help with the complexity. It's still p to the 6th power because you have 3 loops for the n and 3 loops for the k. Okay, but if you use this thing called spherical harmonics, if you read a 3D FMM paper, the first thing it will explain to you is the spherical harmonics. What this is actually, it's like the same Taylor expansion but in spherical coordinates. But it uses like the rotational symmetry of the sphere to reduce the loop count. So before you had to loop over x, y, and z, but now these two angles are associated with the order of r. So you only have 2 loops to loop over these 3 numbers. So it reduces the complexity to p to the 4th. Also, there's a technique where you take the spherical harmonics expansion, rotate it so that it aligns with the axis of the M2L translation vector, and then you can skip the loop of the actual direction, and that reduces another loop, so now you're down to p to the 3rd. You can then also use FFT. So say that this spherical harmonics translation matrix can be expressed as like a lower triangular matrix. You take this lower triangular matrix, you apply FFT on it, and it turns into something that looks like this. And then you do the translation, which is now p squared. And so this translation and scaling are of the order log square p times p squared. So now you've reduced it to this much. And also there are other ways that you can use plane wave expansions to do the same M2L translation. So these are all methods to accelerate the M2L. So this is M2L acceleration techniques. But I'm just explaining this to you because it's related to the accuracy and the calculation trade-off. So these can give you higher accuracy with a lower computational cost. But if you don't want that higher accuracy, because the constants in front of these functions are quite large, they come at a cost. So say that you compared spherical harmonics rotation, this one, with the Cartesian Taylor expansion. So if you actually time the calculation time per cell pair of the M2L interaction in microseconds, you actually see this kind of behavior. So when you increase p, this one eventually will increase as p cubed, and this one will increase as p to the 6th. But when the p is sufficiently low, the low order terms have a bigger constant, so they dominate, and you don't see that p to the 6th or p to the 3rd behavior completely. And also, the one that has worse asymptotics is actually faster because the constant in front of it is smaller. So you don't necessarily see faster behavior just because it's asymptotically better. This is not the case because p you don't want to make infinitely large, or p is not something you are interested in scaling. It's the problem size that you want to scale. So this is about the faster expansions. And now going back to the accuracy issue. So we want to know what the balance is between increasing p and increasing theta. And that's sort of why we want to independently control these two variables. So I did an experiment where I increased the p to like 3, 4, 5, 6. Right now the code you have in the step 1 through 7, it's actually p equals 0 code. So you're stuck with p equals 0 unless you code one of the expansions that I showed in the previous slide. But for the sake of explanation, this one controlled it to 3, 4, 5, and 6. And then the error, which is like the L2 norm, relative L2 norm of between the difference using the FMM and calculating it directly. So you can say this one has 2 significant digits of accuracy, and this one has like 3 significant digits of accuracy. And as you increase p, you can afford to use a larger theta. So if you also decrease theta, the accuracy improves. But for a given theta, so say theta is about 0.7 here, but about 0.7 here. But since you're using p equals 6 here, you get a much higher accuracy than using p equals 3 here. So it's like a balance between the two. But if you look at the time it takes, 0.016 seconds, 0.012. So there's a combination of p and theta that's the fastest. In this row, you see that this 0.012 is the fastest. So you want to use p equals 4, and theta is 1.18 for this accuracy. But for example, this one is the fastest for this accuracy. So if you want 3 digits, you can't just keep using p equals 4 and just decrease theta. Or you can't just keep using the same theta and increase p, because there's always ideal combination between the two that gives the... So here, already, these two are equal. So if probably in the next row, if you want 6 significant digits, this one would probably be the fastest one. So the higher the accuracy, the more towards increasing p you move. But still, the theta value is also something that you want to control. So again, the definition of theta, you can see here, is it's the thing we use for the Taylor expansion. So we assume that the distance between, for example, this xj point and the center point that's shown with the green star is much closer than the point you're expanding to. So this was the criteria of the original Taylor expansion. And this needs to be smaller than 1. Okay, so that's, I think, about what I wanted to explain about the accuracy. Okay, so the rest is sort of not related. It starts to involve MPI. So I'm going to stop here for today's adoptive tree structure lecture. And then in the hands-on for today, I will try to first... So we did in step 7 the Morton indexing issue. So that was introducing the sorting was step 7. But then once you sort the numbers, you can start to do this kind of cell skipping calculation. So let's see if I can code this map between these two to make the code more memory efficient. So because we already have a multi-level code that is somewhat adoptive, it's probably quite easy to introduce this concept now into step 7. And so once we can do that, I think if we have enough time, because we have 2 50-minute sessions, so if we can do this fast enough, I will try to introduce the mathematical parts into the FMM. And then basically we're done with a serial FMM code. So I'm going to try to introduce, so maybe go back to step 1, but do it, where's the, yeah. So this was step 1, but I'm going to introduce these guys into step 1. Not use the complicated one, but go back to the easy one, and then introduce this complicated math into the easy code first. Once you can do this in the easy code, then step 1, 2, 3, and 4, I think, are still single-level codes. So they only need P2M, M2L, and L2P. So gradually introducing that into the slightly more complicated step 2, 3, and 4 should be very straightforward. And then finally, maybe we won't have time today, but if we can introduce the multiple level case with these kernels, then you will have a controllable accuracy code. So basically, if you came to this lecture wanting to have applicable FMM code, by the time we finish this, then you can apply it to actually your real applications, because now you have controllable accuracy, your level is controllable, it's adaptive, and you can use any kind of number of points, because it's also a variable in your code. So basically, by the end of this, you will have everything you need. And now, from there, it's just a matter of coding efficiency and using less memory, or adding more parallel calculations. So we will try to introduce, maybe if we have time in the final hands-on session, some parallel calculations. If you want, we can do some GPU calculations too, because this simplest case. So if we are able to code today this very simple one, I think it would be fairly easy to just do this on the GPU. And then once you have this on the GPU, because you have all the other combinations of steps by this time, it would be easy for you to extend this easy GPU, this step 1 GPU code to this other ones, because you have all the ingredients and you just need an introduction. Okay, so let's try to first do the adoptive tree after the break. So we'll have a 10-minute break again. Start from maybe 11:20, and first do the adoptive code. Okay, thank you. The third hands-on session, and I spent the first part of this morning explaining sort of the hands-on review. So I think we can continue from where we left off this morning, which is step 7. So the goal is to get, let's see, the adoptive FMM we want. So right now we have these features. So step 7 was doing the sorting of the bodies thing. So how does this relate to the adoptive thing that I described today? First, the level offset doesn't assume the adoptive tree at all. It assumes that it's actually full. So the level offset we calculate in step 6 actually uses, you can see in the function how it's not adoptive. So when I calculate the level offset, I'm saying here that the number of boxes in each level is 1 bit shifted to 2L, which means it's like 4 to the Lth power. And this means I'm assuming that the tree is full. So same here, n cell being nx by nx is assuming that the tree is full. So I want to gradually move to a code where this skips the empty boxes and this also skips the empty boxes. We have the ability to skip empty boxes here because what we did was in step 7 we introduced this sorting of. So once we perform this bucket sort, this I cell was printing the Morton index in order and it was jumping, right? So now we need to only detect, because it's in ascending order but jumping, we just need to form a loop for all the bodies, calculate the new I cell, which is in order, and so every time it changes, so this is trying to detect every time it changes. How do we detect if I cell is changing? Well, so if it's not similar to IC, we go into a loop where it defines a new cell, and then we update the IC so that it's equal to iCell. So as long as iCell is the same as the last time, it will not go into this loop again. But then once it changes, then this will become not equal again when iCell jumps to a different value. So every time iCell becomes a new value, so it's like 9, 9, 9, 9, and then 11. When it becomes 11, it goes into this loop again, and then it increments n cells. So it's counting how many cells there are. It's starting from 0, and since IC is set to -1 initially, iCell is never -1. So in the first loop, it will go into this if statement, because IC -1 is not equal to iCell, which the first number I think was 1. And so it first substitutes IC into iCell, and then this is the thing I was talking about, the map between the continuous index and the Morton index. So this n cell is actually the continuous numbering that I showed in the slide. I had a number that was not jumping. I think it was somewhere in this one. So yeah. So this numbering here, 0, 1, 2, 3, 4, 5, 6, 7, 8, is this thing n cell, because it's being incremented by 1 every time it goes into this loop. So it goes into this loop every time it goes into a new iCell index. So it's iCell here, this array contains these numbers, 0, 1, 3, 8, 10, 11, 13, 14, 15. And this n cell contains this number here, 0, 1, 2, 3, 4, 5, the continuously incremented number. And by saying cells, n cell equals IC, I'm actually creating the correspondence between, so every time I input here, these numbers here, it will give me back from this side, it will give me back this number. So in the end, once I finish this, what I can do is, instead of looping over from 0 to 15, I can loop from 0 to 8 and then put the index of that loop into this cells operator. It will give me back the proper iCell number. So it's as if I'm looping from 0 to 15 and skipping the empty boxes. So I can create a loop from 0 to n cell, which is 0 to, like loop from 0 to 8. Okay, so now I have this here, but I haven't changed anything below. So I will start to implement this this jumping index routine, and I will check every time that the answer is not changing. So a good thing about doing this incrementally is that I can run this, and I'm actually suppressing the output right now. So I should print the answer so that I know that it's working correctly. Okay, so now if I run this, it will show. So everyone, you can download from the website, because step 7 I've uploaded to the Google Drive. So everyone can download this same code and see that it's matching 209, 209. So it's a good match. Okay. So now let's start to use this array called cells, and let's try to use it here in the P2M part first. So instead of looping, well, maybe this is better done by just leaving it alone, because it's already, so P2M, you can do it two ways. You can loop over all the bodies and sum to the appropriate cell, or you can loop over all the cells and then have another loop going over all the bodies inside each cell. But maybe it's much simpler if you just loop over all the bodies And since they're in the order, the cells are in order because I sorted them, it will execute quite efficiently if I just leave it alone. So maybe I won't touch P2M. But here, M to M, maybe I can start to modify. So this loop here, N cell, is obviously looping over the multiple expansions that are all 0. And it's adding 0 to, that's unnecessary. So let's see if I can change this so that it loops over. So so let's see. Maybe I should use a different name here because N cell is being used somewhere else. Let's call this leaf because essentially what this is it's the number of leaf cells in the tree. So let's call this N leaf. Okay, so I'm going to try to use N leaf in M to M. Okay, so instead of N cell, I'm going to use N leaf. But then, if I just use N leaf, it's not going to work. So I need to use this map cells that we defined. So let's see. So just to show you it's this thing here, the cells that we defined here, which maps the continuous index to the Morton index. Okay, and maybe I can call this J or something. So now the I's turn into J's, and so what I changed was this was looping from 0 to N cell, which was looping over from 0 to 15 and going through all these empty ones. But now I'm skipping the empty ones by looping only from 0 to 8, but using these cells to map the 8 to 15 and 7 to 14. So it will look like I'm looping over these numbers and skipping the ones that are not there by doing it this way. So let's see if this gives the correct answer. Okay, the answer didn't change. See, it's still 209, 209. All the numbers look very similar. Okay, so what we did is we successfully changed M to M to use the cells. Okay, now let's do the same thing here. So I'm going to loop over leaf, but then instead of using I, I'm going to use cells I. And here also, I will loop over just the leaf. Oh wait, this won't work because there's one problem. So this M2L is going from level 2 to level 3. So the N leaf only works if I'm at level 3. So when I'm at level 2, I need to do something else. I need to find, so I know the map between these numbers at the bottom from 0 to 8 to 0 to 15, but M2L is actually, when it's at level 2, it's looping over these boxes up here. So this one, and this one. I need to have a map from, like the continuous index of these larger boxes to the Morton index of these larger boxes here. And I have not created such a thing. So I still cannot use it for the M2L. So maybe I'll just leave it alone for now until so I need to update the level offset to be able to do that. But however, I can do it for the L2L part. So I can, because this is essentially only doing level 3, the bottom level, I can actually loop over leaf and then use the same way. I can use cells I and then just change this to j. Okay, so this one should be, and then now I don't need to do calculate n cell. Okay, let's see if this, okay, so still we have matching answer. So this is working. Okay, now let's see if we can make this part more efficient, because this P2P, what it's doing now essentially is it's looping over all the points and also all the points, and then inside that it's determining if they're neighbors. So this is not particularly efficient, because algorithmically this is like an n square calculation where it has to loop over everything against everything. So it's not very fast. Ideally what we want to do is to just loop over all the non-empty the leaves, and then loop over all the bodies inside them for both I and j, and then calculate this ix and jx. No, we don't have to calculate the ix and jx. We just determine their neighbors. So let's change the structure of P2P based on the new sorted index we have. Okay, so how can we do this incrementally? So we can loop over 0 to n leaf, and then we first determine like the cell index of IC, of the I points, and then we don't do this calculation yet. We use the get ix function. So have I used get ix somewhere else? Yeah, it's being used like this. So actually, maybe I won't define this intermediate value. I can directly say I want ix from cells I. This is more efficient. I think ix is defined somewhere in the beginning, right? Yeah, up here. So it's okay. I can use ix. So now, without doing this calculation, I already have access to ix. And then, instead of looping over j and trying to see if, maybe let's try this first. So, because it requires least amount of modification, I'm going to do this instead of this. And then this will determine if it's neighbors or not. The thing I don't have is I need to loop over, how do I find the index of the bodies for I and j? So I can't use this I and j to determine dx and dy. These are, I changed this to mean the index for the cells. So they're not the index of the bodies anymore. So I need to change something. So something is missing here. We need to go back to this part where we are calculating the cells. And I need to calculate something called the offset we defined. So this could have the same size as the cells, but I need to calculate this offset thing here. So what is the offset? The offset is the thing I showed, not here, but I guess it was a long time ago. It was in the second day's slides. I introduced this concept of offset. So this is what I want to calculate now. So what was the offset? The offset was this once we have the sorted index, I want to know the index where it changes the number. So offset 0 is 0. Offset 1, it changes at 1. And then here it's the same number, but then at 3, again, it changes to 2. So I want these numbers where it switches, because from this number, I can retrieve the index of the, the x and y I need to loop over. So, and this can be calculated in the same place I'm calculating this thing here, because offset is basically I whenever IC and ICell are not equal. So offset 0 I can initialize with, so let's say offset, or no. It needs to be outside this I loop. So offset 0 is always 0. And then whenever n leaf increases, so offset for 1 is I minus 1. So for those of you that didn't follow the logic here, what I'm doing is, because this becomes not equal one step too late. So offset 0 I know is 0 because the beginning is always 0. Then by the time IC is not equals ICell, I'm already at the next index. So what I want is the index before it switches. Or no, do I want the... So n leaf is 1 at this point in the first loop. And I want to know when it... Do I want to know the... no, sorry. I don't do this here. I can actually do it like this. Then it makes more sense. Okay. So this is easier because in the first loop it's 0. N leaf is 0, and then it will input 0 because this will be executed. This if statement will be true in the first loop. So this will be 0. And then the next time it switches, this will be 1. And also this will be 1 because it's, well, if it is in this order. And then when the 1 continues twice, it will count, the n leaf will move. And then I can input this offset 3 because I will be 3 at the time. Okay, so I think this is the correct offset. Okay, so by doing this, I will have all the offsets, but I need one more. So actually, what I need is offset n leaf equals n, just to finish, because I need the offset n leaf, this final offset, to be pointing to this very end n, because I'm going to use this offset plus 1, like I plus 1, to mean the end of the loop. So I need to add this last thing here. Okay, so now maybe I can test this with P2M conceptually, because although this is not necessary, I can test So this is where I use the offset. Offset and then I don't need to do these things. Yes? I think this is, and I think this needs to be cells. Okay. Is this correct? I think so, because what I did was I'm looping over all these jumping indices now, so I need to change I because this needs to be the Morton index. Level offset can remain the same for now, although later on I can also change this so that it uses the only the non-empty level offsets. But for now it's fine, and then J should be from offset I to offset I plus 1, because I want to go from here and not including, so this is less than offset I plus 1, which is the beginning of the next index. So that's should be the terminating criteria for the loop. And this is why I had to do the offset n leaf equals n. I needed to add this last thing because when this reaches the end of the, when reaches the end of this loop, it will access offset n leaf. And there needs to be a number in the final loop. Okay, so let's see if this works. Oh. I think this is just a warning. Oh no, the number changed. Okay, so I think I did something wrong. Do I need a... Yeah, I'm not sure what went wrong. Well, first of all, I think I offset 0, and I'm going to n leaf equals n. Yeah, this should be okay, no? Did I change anything in P2P? Not yet. Ah, no, that's right. I did change something here. So, yeah, this is why it's giving the wrong answer. I was sort of in the middle of changing this, and then I realized that I needed the offset, and then I went back and changed the offset, but forgot to come back here and use the offset for these two calculations. So, yeah, I want to use the indices I and j for the bodies themselves. So I'm going to define, did I define IC somewhere else? Well, I'll see. Yeah, I want to use IC for the cells and JC for the J cells. And then I can use I and j here. So I need to loop the offset. So this is the same thing as the P2M case. So it goes from offset, whenever I know the cell index that comes from n leaf, I can use that to access all the bodies inside that cell. So same for J. Offset JC and J is less than offset JC and J plus plus. Okay. And then I can just do this same thing. I think this should work. Maybe I defined IC somewhere else. No. Okay. Ah, yes. I defined it here. So I don't need to define IC. Okay. So let's see if this gives, because right now this side is giving a different number from before. It was 209, but now since I screwed up the P2P part, it's not giving the correct, but, okay, so there's something still missing here. I changed IXJX to ICJC cells ICJC. Qi and j, and j is offset
offset IC plus 1.
where
The whole loop. The I are all the same. IC and smaller than IC.
this one,
The inner for loop.
this one,
Yeah.
offset IC to plus 1, okay. Yeah, that's I think that's necessary. Okay. Oh, good. Yay. Very good. So now we have a matching answer. Thank you. Okay. So, yeah, maybe we can also change L to P, because we changed P to M, and now it looks a little bit simpler than before. So let's do the same thing to L to P and see if it will look simpler. So we don't need NX and NCell anymore. We will loop over I leaf. We don't need these things. And we need to loop over offset I, and I need to remember to do plus 1 here, plus 1. And I think this needs to be cells. Okay, I think this is okay. Let's see. Yes, good. Okay, so now I'm using the advantage of cells. So in L2P, I'm looping just for the non-empty cells. Also in L2L, I'm looping over just the non-empty cells. And except for M2L, M2L I don't know how to do yet, but for M2M and P2M, I'm looping over the non-empty cells. Okay, so now maybe we should just call this the end of step 7 because it's working fine. I'm going to now copy this over to step 8 and step 8.c. And I will upload step 7 to the Google Docs. So in case you want to see the entire code better on your machine, you can just copy over to the Google Drive step 7 to your local machine. Okay, so I copied to the Google Drive. So step 7 is available online. So now we will work on step 8. So we want adoptive tree. So step 8 is like the full adoptive tree. The remaining thing that we need to do is the M2L is still looping over N cell, all the cells against all the cells. The problem was because it's looping for level 2 and level 3 both, I can't just use the non-empty cells at the bottom level. I need the non-empty cells at the upper level. So how can I obtain such a number? And the key, I think, is actually in this level offset function. So if we define this level offset function careful enough, it will actually serve the purpose as the number of cells, the number of non-empty cells at each level. Except, so if we're going to do that, we need to have this map at every level. So this cells thing, we need to call for every level so that it maps. If I show the adoptive picture for you, you'd be able to understand better, I think. So let me show you the picture of the two adoptive trees, this one. So what I'm thinking is this, sorry, it's the side of the screen is a little bit shorter than my screen. So what we need is, so not just at the bottom, but we need to know a map between, so in terms of Morton index, this would be 0, this would be 2, and this would be 3. But in the continuous index, this would be 0 and 1 and 2. So we need to map 0, 1, 2 to 0, 2, 3 in this level 2, not just the level 3. So this can be done by carefully constructing level offset. Level offset right now is being set to like full tree. But if we set this so, and also the cells in array, these two things we will change so that level offset first will only count the non-empty. So it will skip, for example, this node here at level 2 and skip all these missing things at level 3 in the level offset. And also, for the cells map, we need to map not just at the bottom level, but also at level 2. We need to create a map between IC and nleaf. So how do we do that efficiently? Let's see. So we can put this entire loop where we calculate, the cells and the offset, but the offset we only need at the bottom. So it's really the cells that we need to calculate again. And once we have the cells at the bottom level, actually we can use that to create a loop that loops over only these non-empty boxes. We divide that by 4, and then we do something similar to here. So it's like we loop over 1 to nleaf and look at cells in the same way that we're looking at iCell here. And when cells changes, that means you're at a new parent index of cells. So we do cells divided by 4 equals IC or not, and then we do something, and we do that inside this loop for the levels. And we can do that simultaneously with the level offset definition here to make, so we sort of first make cells into a multidimensional array here and call this cells at level 3 definition, and then we need to do the same thing for cells at level 2 and so on in this function here. So let's first make cells into a multidimensional array. So I'm going to put cells level +1, and now I need to make sure I change all the cells so that right now what it's doing is it's essentially doing cells at level L. Also here level L, and here level. Here also bottom level, so it's level. So I'm just doing like a search and replace thing for all the cells entries, and I'm going to check that this code compiles after I change this one thing. I made cells into a multidimensional array, and this I have confirmed that it did not break the code. Okay, so now that cells is a multidimensional array, I can make the next level map by changing this to level 2 cells, and this will be like the non-empty entry at the level 2. Okay, so let's leave this part alone because this part is necessary anyway. So offset is only valid at the bottom level because we only access the bodies inside the cells at the bottom level. And we need to know the cells map at the bottom level to efficiently construct the map at the higher levels. So this part we need anyway. We're going to leave it alone. But then we are going to create a loop over the levels that creates the next level of non-empty cells, and maybe we can also use that to define the level offsets. So yeah, first we need to here, before we define the level offset, we need to know this cells thing. So we do the cells at level, let's see, so we loop backwards up to, I think, level, yeah, we can loop all the way to level 1. Oh, no. Like this. And so this is going to be used to calculate the non-empty cells. So I'm going to do, for each level, I need to initialize the counter to some number like this, and then I loop over the cells. So there's and leave, or no. Yeah, how do I determine how many? Maybe for now I'll just assume that there's only one level to go. So if I loop from like this, and yeah, and then do something like this, cells divided by 4, and do the do the same thing I did here, except this is not n leaf, this is like n cell per, I don't need the offset. Equals 0. Yes? And then I just need to put this inside a loop that goes backwards, because, and I need to somehow make this n leaf become the old n cell before it's initialized to 0. And then I think this will work. But for now, because we only have level 2 and 3, I think this is enough. So what this will do is it will give me, no, I need to change this to level, cells level divided by 4, and this needs to be cells level minus 1. And this will create a map to all the non-empty cells at level 2. Yeah, so maybe I don't even need to modify level offset yet. I can just leave this alone. All I needed was this cells, the map at level 2. And this will give me that. Right, because I loop over all the non-empty cells here, going from like 0 to 15, and every time that number changes, it will give me a new IC, and n cell will be incremented. And so n cell will be the number of cells at level 2. Yeah. Okay, so what I can do is make n cell actually an array that contains the index of the level. And then n leaf can be n cell at level 3. Right? And then, yeah, I guess everything else will... yeah, I think that's the best way. Okay, so now I think it's about 50 minutes into the... So here, we'll take a break, and those of you who haven't been following too well, you can ask questions during the break. In case you want me to show a different part of the code, I can shift the screen up or down. But we'll take a 10-minute break now, and then continue with this so that we can have fully adoptive FMM. And if we have time, the last thing we need to do, like I mentioned, is to introduce those high-order kernels, which I have already prepared. So it requires just changing a few parts in the code where you have M and L into like a cell structure, and just calling the kernels that I've prepared for you, and then you'll have the high order calculation. The rest of the code won't change too much. Okay, so let's take a 10-minute break and resume with this in 10 minutes. Okay, thank you. The hands-on session. So we will continue with this cells, level-wise cells map. And I was going to change this n cell into array for each level. And then n leaf is essentially n cell at level 3. And so these numbers here will change to array. And I'll do that first. And then I can put this whole thing inside a loop, because I need to do this for every level. So say, right now we have only 3 and 2 level 2 and 3, but in a deeper tree we will need to do this for all the levels. So to make it applicable to any level, I will first change n cell to be, where do I define? Okay, so it's actually not defined. And so I will define as a level +1 dimensional array. And yeah, maybe I can just initialize this to be like all zeros or something. And then n leaf, every place I say n leaf should actually now say n cell level. So I'm just going to do like a search and replace thing here so that it doesn't. Okay. I think I just changed just one part of the code. So I made n cell into a multidimensional array, and then I changed all the n leaves to say n cell level. I haven't changed anything else yet. And yeah, maybe I should check first before I do any of this thing here with the cells. Maybe I should check if the code still works, because it should still do the old thing that it was. Oh, okay. So I changed some. I have definitions of n cell that conflict. Oh, I see. I haven't changed. No. I shouldn't do this. So actually I don't need this here. And this one I do need. Okay, but I shouldn't define this here. That's the problem. I should define it more like up here. So I need to define what n cell 2 is. Okay. And also this thing here, what can I do? Level offsets. I think it's okay if I just do here level without defining it here. Oh, I'm using NX here. Okay, I think everything else should be good. Oh, variable size object. I need to initialize the n cell somewhere else, like this. And L is undefined. Oh, good. Oh, no, okay. There's something wrong. Oh, it's yeah, it's this thing here. This needs to be the full index. Okay, I think this. No, there's still something. Yeah, I think there's something wrong here. Oh, no. Okay, I think I made too many changes. I'm going to start from just changing n leaf to n cell. Okay, so now if I just change this to n cell level, nothing should change. Okay. Okay. Good. Now Okay, one change at a time. I have now only changed one thing. I changed n cell to have level-wise index. And I changed all the n leaf in step 7 to n cell level. So now what I need to do is remove these n full things. This is the only thing I want to change ultimately. So n full I want to change to the n not full. Okay. And now, the second change is I want to make cells into a level-wise index. Okay. Okay, good. Now cells has level information. So now I'm ready to change to loop. Okay, loop, starting from the bottom, loop over the cells and do the same thing as this one. Okay, cells level is L minus 1 and cell level minus 1 IC starting from minus 1. Okay, so this should give me all the maps and all the n cell non-empty cells at each level. And this should not affect the execution of the other parts of the code. Yes. Okay. So since it's working, I'm going to upload this to the Google Docs so that you can download and see what is happening to the step 8. Okay, I've uploaded step 8 up to now. But I'm not done yet. So the last change is to change this n full, so all these parts that have the full index, into, yeah, especially here in the M2L, what I wanted to change was this looping over the full Morton index. Instead of doing that, I want to access this I with cells at level L, I, starting from the n cells index at that level. So the non-empty one, I want to loop over the non-empty cells, map that to the Morton index, put it in to get XID, and same here. And I don't think I need to change anything else if I just change, yeah. So I just need to change this one to n cell at level L, and put here cells level L and I, so that, and I can delete this part here. Okay, so let's try changing all the n full to n cell. So here I no longer need to define n full, because now n cell at the bottom level is what I need here, and cell level, I don't need this here, and cell at level L, and then cells L, I, same here, cells at level L, and cells L of J. Okay, so no more full index. Oh wait, I think I still need the full index here, because really? Yeah. I need the full index here. Okay, let's see if this works. Oh no. So something I did here is not working. N cell Oh, okay. So I think I'm redefining the index I and J. I don't know why it was working before. But it shouldn't have been working, because I'm defining I and J here, and I'm using those as the loop counter here. So that was not correct. Okay, now let's see if this is working. No? Okay, I'm going to revert back to the thing that was working on Google Drive. Oh, this is not synced. I don't know why. Okay, I think this version was working. Yeah, this version is working. This is before I did So it's after I changed everything to level-wise arrays. But before I change the M2L thing here. So there seems to be a problem when I change this to the non-empty index. So it needs to be the full index for reasons unknown. But first I found a bug here. So this already has a bug. This I is being used here and also in the loop counter. So this is wrong. And I need to fix this. So I'm going to change this one to IC and this one to JC. And then I will upload this to the oh, I see what happened. So yeah, because it's the full index, I think it becomes the same thing when I do get index. Yeah, right. Because I do get IX here, and I use that IX to do the get index. So of course, if I change it back and forth, then I should be the same as the loop counter anyway. I see. Okay. But this should be working. Or no, this doesn't work. So that's strange. Ah, it's because I'm missing here. Yeah, good. Okay, so now I will copy this to the Google Drive. Okay, Google Drive is syncing. Oh, good. Okay, now it uploaded. So, yeah, maybe I should do this gradually. So if I change this just one part to N cell L, yeah, so what happens if I do this? No, it doesn't work. Okay, I think something is wrong with the let me change this back to the working state and full. So this should give the correct answer, but I think something is still wrong here with the cells. Divide by 4. Ah, I see. I need to have this here. That's why. So now I think I can get this to work. This should work. No? Okay, there's still something wrong. Okay, something is not working for this calculation. Oh no, this is not I cell, this should be cells. Okay. Now I think it should work. Oh, good. Okay. Finally. So now we have the M2L part working with non-empty, the adoptive numbering. So I no longer need the n full here. Yes. And also, let's see if I can. Yeah, I still have to index the M and L arrays with the full Morton index. I wonder what I can do about this. Okay, but anyway, I'll upload this working version because step 8 is now working as it should and ready to, yeah. Okay, now uploading to the okay, so just one last thing I want to do is to change this full index that's being used here to just use the non-empty index. So for here, it's okay because I can just use I instead of this cells I. But here, yeah, here I can also use just I. But for the parent, I'm not sure because I can only find the parent if it's the Morton index. I can't find the parent. So it's because I don't have the inverse map. So I can only go from 8 to 15. I can't go from 15 to 8 right now. I know the number 15 and I want to retrieve the 8, but I don't have this number. So that's why I can't. I have the number 15 for the parent, but I can't identify what number. So I need to just create a reverse map of some sort. So here, where I am defining the relation between this number n cell and IC, I need to have another map that says here IC, and on this side it says n cell. Then it will be the map in the other direction. So I just need to create another thing here that is sort of a map in the other direction. Okay, so maybe I'll call that cells 2. So this one is map in the other direction. And I think this needs to be initialized to like -1 or something because Okay, for this is just for the initialization of cells 2. Okay. And then I do this for other levels. Okay, let's see if this works. Okay, well, I haven't done anything. I just defined cells 2. Okay, now how do we do this gradually? We can do, yeah, if I change this to I and this to I, maybe it will work. No. Also change, yeah, I need to change a bunch of things actually. Cells 2, like this. Yeah, I need to change all the M index. Like this. No. Okay. Yeah, something is not working here. And I am not sure what it is. But cells 2 is not working very well. Oh, I think I know what happened. So there needs to be like a conditional statement saying if cells 2 is not like -1. Like this. If this works, then the rest of it will. Oh no, it's still not working. Cells -1. Mhm. Okay, well, I guess maybe this is okay. Yeah, but I think it's necessary to have the non-empty index here. Well, maybe this is good practice for everyone. Just see if you can solve this issue of how you can index the M and L arrays with the non-empty index. Thank you. Thank you. Okay, so let's see if that's true. If everything I said is correct, then I should be able to do something like this. Level offset. Because n cell is basically the number of cells in that level, and the offset should just be increment based on the number of cells per level. So this, by definition, this should work like this. Ah, good. Okay, so I'm getting the correct answer. That means everything. So in FMM, unless everything is working, the answer becomes somewhat different. So you always know that everything is working if the answer is correct. So, okay, now this is a real step 8, the adoptive. So I'm going to upload finally the final version. Okay. Okay, good. So we still have 2 more days. So we haven't done anything in parallel yet. So maybe I can do some. In the lecture tomorrow, I'll talk about the parallel stuff, and on the Friday lecture, I'll talk about some matrix, H matrix, the hierarchical low rank approximation methods, which is like the matrix form of the FMM. So until today, I discussed FMM like it was like an n-body solver. But actually, you can use FMM, the concept of these trees and compressing the data and approximating the far interactions. These can be viewed in the form of a matrix. And since many of you will be using matrix solvers, I will show you how this technique that you've learned can be used as a solver in the final lecture. So tomorrow is parallel, and the day after that, Friday, is matrix stuff. Okay, so thank you very much.
好，3天了啊，开吧，剩2个，那明天引起后天那个。